All right, so we're going to be considering bundles over x and y, which have the following utility function. It's going to be the minimum of 3x and 4y. So this is a type of utility function that's referred to as perfect complements. So what it means is that the utility I get is going to be whichever, it's basically going to be whichever I have the least of. So I get 3x and 4y, and I just take the minimum of those. So this is what we call perfect complements. So it means that I want to consume goods x and y in a particular ratio. So I don't get any additional utility if I have like more y. I want to consume x and y in a fixed proportion. So an example would be left shoes and right shoes. I don't care about having 2 right shoes if I only have 1 left shoe. Or another example I like to use is hot dogs and hot dog buns. You really consume one with the other. You don't really generally consume them separately. So this is what we call perfect complements. What we want to do is to consider what happens when we're given price of 2 goods. So we have the price of x is 2 and the price of y is 5. So I'm just going to write, these are perfect complements. Or I should say consume in fixed proportion. All right, now for part B. Sorry, I got a bit ahead of myself there. So we have price of x is 2 and the price of y is 5. And the income of the consumer is 50. So what we're going to do is we're going to draw the budget line, just like we did in the previous problem. So this is going to be our consumption of good x. This is be our consumption of good y. The budget line is going to be a line with the slope negative 2/5, I believe. So just to find that, just to walk you through how we do that, we get 2x plus 5y equals 20. So this is our budget line. The way we derive this as a function of y in terms of x, we just have 5y is equal to 20 minus 5x, or minus 2x, my bad. And then y is equal to 4. I just divide the 5 minus 2/5 x. So we can see that this is a line with intercept 4 and slope of negative 2/5. So graphically, the budget line is going to look like this. Okay, so this is our budget line. Now we want to find the optimal choice. So when we're looking at perfect complements, one thing that we know is that they're going to have sort of a kink. So they're going to look something like this. This is not a differentiable utility function because of this corner right here. Like I said, there's a kink. The reason why is because my utility of, say, this bundle, which is given by the minimum of 3x and 4y right here, we can see that this is going to be the same as the utility here. Because I just increased the amount of y, or I increased the amount of x, but I didn't increase the amount of y. So my utility is the same. So that's why they have this shape. I'm going to more carefully plot this. So the utility of x and y is the min of 3x and 4y. So the kink of this utility function occurs at the point where 3x is equal to 4y. So We'll see why in a bit. But this just means that y is equal to 3/4 x at the kink point. So at the point where it's a corner. So if we want to plot this, we note that it's just going to be a line with a slope of 3/4. So it's going to be sort of like this. So this is the equation which shows us the kink of the indifference curve. Now I'm actually going to plot it. So I'm going to plot a variety of indifference curves corresponding to this utility function. So what I did was I just identified the kink point of each line. Actually, that intersects with my budget line label. So I will erase this. So we can see that the utility function looks like this. Because at each point on this purple line, the minimum of 3x and 4y is just the same, because we set 3x equal to 4y. So this line, I just rearranged this formula to get this, describes the point at which 3x is equal to 4y. So this is the set of all points for which that's true. And then for any point, if I increase, like, say I'm here, and I increase the amount of x I have, but I don't increase y, I don't get any more utility, because I started at a point where 3x was equal to 4y. So that's just showing you how to plot these indifference curves. Now, what we're going to have is for these preferences, the optimal consumption for the consumer is to just consume at the kink point. So they're going to consume at this point that intersects where the indifference curve touches the budget line. And this is going to be precisely at the kink. So what we're going to want to do is we're going to want to find so we want to find the point on the pink line, this one right here, which also lies on the budget line. So that means we just plug in, mathematically we plug y is equal to 3/4 x into the budget line. So the way we do that is we just say, okay, px times x plus py times 3/4 x is equal to m. So what we get, if we rearrange this, is we say px times x plus 3/4 py times x is equal to m. If we factor out the x, we get x px plus 3/4 y, or 3/4 py is equal to m. So then x is equal to m over px plus 3/4 py. So this is our optimal consumption of x for a given income, price of x, and price of y. Okay, so given this, we may want to find the corresponding demand for y. So we know that y is equal to 3/4 x. So this means when we plug in this optimal value of x, we can find the optimal value of y. So y is equal to 3/4 times m over px plus 3/4 py. So this is m, 3/4 m, over px plus 3/4 py. All right, so this is our optimal consumption of y. This means that I'm just going to indicate the optimal consumption with a star. So the optimal consumption at income m and prices px and py is going to be consuming m over px plus 3/4 py, and then 3/4 m over px plus 3/4 py. So this is the optimal consumption. Now what we do is we're asked what happens when px is equal to 2, py is equal to 5, and m is equal to 20. So this means that x star y star is going to be 20 over 2 plus 3/4 times 5, which is just going to be 15 over 4. And then the consumption of y is going to be 15, because 3/4 times 20 is 15, times 2 plus 15 over 4. You can simplify this further if you want, but this is going to be your answer to this question. You don't need to necessarily do all that algebra. All right, so that's part B. What we now want to do is we're going to fix px and m at the previous values. So we're going to have px is equal to 2, m is equal to 20. Then we want to find the optimal quantity of good y as a function of py, and then find the demand curve. And then finally, we want to find the price elasticity of demand for y. Okay, so 3 parts. First, we're going to fix px and m. Then we're going to obtain the optimal quantity as a function of py. And then we're going to find the demand curve for y. Then finally, we're going to find the price elasticity. So we kind of made our lives easier here because we solved for x star and y star as a function of all the variables. Now we just need to plug in m and px, and then we have these as a function of py. So we already did that work. So for part C, we plug in px is equal to 2, and m is equal to 20. And then all we need to do is we want to, 1, find y as a function of py. 2, we want to find demand. So this just means we flip the graph and we find py as a function of y, basically. So we plot y on horizontal, py on vertical. And then finally, we want the elasticity of y. Okay. So the way we do this is first we want to find ypy. The good thing is, like I said, we already found the equation for y. We have y of py is up here, we know that it's 3/4 m over px plus 3/4 py. We just substitute in m is equal to 20 and px is equal to 2, and then we'll have the amount of y consumed as a function of py. So it's going to be 15. Well, yeah, so it's 3/4 times 20 over 2, because px is 2, plus 3/4 py. And I can simplify this. It's just going to be 15 over 2 plus 3/4 py. So this gives us y, the optimal consumption of y, as a function of py. Sorry, I didn't mean to erase that. So we did the first one. Now we just need to find demand. So what we're looking for when we're saying finding demand is we're looking to plot y on the x-axis and py on the vertical axis. what we can do is we can first plot the flipped graph. So we plot py, so the independent variable, we plot it down here, and then we plot y of py up here. So what we see is, if we look at this function, when py is equal to 0, this is going to be 15 over 2. So I just want to do some math here. Y of 0 is 15 over 2 plus 3/4 times 0, which is equal to 15 over 2. So we see when py is equal to 0, y is going to be 15 over 2, also known as 7.5. Well, I'll just write 15 over 2. Okay, no, actually, just to be consistent with the posted solutions, I'll do 7.5. So we know that when the price of y is 0, the demand is going to be 7.5. And then we see that as the price of y increases up here, the demand for y is going to go down. And it's going to go down pretty fast because the py is in the denominator. So if I make py really big, this is going to get really small. So it's not going to be a straight line, it's going to be a curved line. Oh no, I did not mean to erase that. Okay, so it's going to be something like this, where the amount I buy of y decreases as the price of y increases. And then for any price above 7.5, my demand for y is going to be 0. So what I do is I flip this. I flip it. And then I plot py as a function of y. So when the price of y is 0, so when we're down here, my demand for y is going to be 7.5. Wait. Oh, sorry. I misdrew one thing. This is just going to be up to here. It's not going to go any further. Sorry, that's my bad. I got carried away. So when the price of y is 0, the demand for y is going to be 7.5. Then we're just going to have this part. Oh no, that was supposed to be curved. We're going to have this right here. It doesn't want to bend. Okay, well, I'll just freehand it. So it's going to look like that. All we did was we just took this graph right here and we flipped it. Right, so that's how you plot the demand curve. Finally, we want to find the elasticity. So if we want to find the elasticity, what we're doing is we're going to look it's defined as the negative dy as a function of py over dpy times py over y. Now, note that I'm doing a negative here because this thing's going to be negative, so I take a negative to make this positive. That's just a convention. That's just part of the formula. So if I want to find the elasticity, I just take the partial derivative of y with respect to y, and then multiply by py divided by y. So here, I have, recall, that y of py is 15 over 2 plus 3/4 py. So dy of py dpy. So the derivative with respect to py is going to be 15 over 2 plus 3/4 py squared. So negative this times 3/4. So that was just the chain rule. And then it's this means that the elasticity is going to be negative 15 times 3/4 over 2 plus 3/4 py, all of that squared, times py over, this should be ypy, just to make it clear that this depends on the price, over ypy, which up here is 15 over 2 plus 3/4 py. So what I'm going to do is I'm going to do some cancellation. Note that these two negative signs cancel, so I'm just left with 15 times 3/4 over 2 plus 3/4 py squared. And then for this fraction here, I'm dividing py by a fraction, which means I can just multiply by the reciprocal of this. So this becomes times py times 2 plus 3/4 py over 15. Again, I just multiplied by the reciprocal. So we get some cancellation here. There's a 15 that goes away. This 2 plus 3/4 py cancels with one of these twos down here. So I'm just going to write it like that. And then we're left with the following elasticity. So it's going to be 3/4 py divided by 2 plus 3/4 py. All right, so this is the elasticity of the demand for y with respect to py. This is the price elasticity of demand for y. All right, so that is problem 3.